Welcome to this lecture on the comparative anatomy of vertebrates. Today, we are going to explore one of the most critical functions of life, respiration. We will look closely at how different animals use their skin, gills, and lungs to extract life-saving oxygen from their environments. By the end of this video, you will understand not just what these organs look like, but the fundamental physical laws that force them to evolve in such incredible ways. Let us dive right in. To begin our journey, we must first understand the physics of respiration. Why do respiratory organs look the way they do? It all comes down to a process called passive diffusion. This is the natural movement of molecules from an area of high concentration to an area of low concentration, and it happens without the body spending any energy. For a tiny, inactive organism, a simple flat surface is enough to let gases diffuse. But as vertebrates evolved to become larger and faster, their internal tissues moved further away from the outside air. Simple diffusion was no longer fast enough. To survive, nature had to invent highly complex, folded structures to maximize the surface area and keep these active animals alive. Now that we understand the concept of diffusion, let us look at the mathematical rule that governs it. This is Fick's law of diffusion, the master blueprint for all respiratory anatomy. It tells us exactly where these organs come from conceptually. The variable R is the total rate of diffusion, meaning how fast oxygen enters the blood. D is a constant, depending on the gas. A is the total surface area available. Delta P is the pressure difference driving the gas, and D is the thickness of the tissue barrier. If you want to increase the breathing rate R, you must either increase the surface area A or decrease the barrier thickness D. This simple equation explains millions of years of evolutionary changes. Let us see this formula in action with a concrete example. Imagine a primitive aquatic vertebrate that breathes through a flat patch of tissue. We are given a surface area of 2, a pressure difference of 10, a diffusion constant of 1, and a tissue thickness of 0.5. We want to find the original rate of diffusion. We chose Fick's law because it directly calculates this rate. By plugging our given values into the equation, we multiply 1 by 2 and then by 10 divided by 0.5. This gives us a final rate of 40 units of oxygen per minute. This low rate means the animal must remain slow and inactive to survive. So we have calculated the baseline rate. This brings us to proving the mathematical advantage of anatomical folding. What happens if a mutation causes that exact same tissue to fold back and forth on itself? The surface area increases to 8, while everything else stays the same. We substitute the new area of 8 into Fick's law. The math shows us that the new diffusion rate jumps to 160 units of oxygen per minute. By simply folding the tissue, the animal absorbs 4 times as much oxygen. This mathematical proof shows exactly why highly folded structures like gills and lungs became the dominant anatomical features in all active vertebrates. Now that we have proven why surface area matters, let us look at the simplest way animals breathe, cutaneous respiration, or breathing through the skin. Think of a dry sponge soaking up water. Amphibians, like frogs, do this with oxygen. For this to work, the skin must be packed with tiny blood vessels called capillaries right near the surface. Crucially, the skin must stay moist because gases cannot diffuse across dry cells. They must dissolve in water first. This is why amphibians live in damp environments. While this method saves massive amounts of energy because the animal does not have to actively pump its lungs, it is strictly limited by the size of the animal's body. This limitation of skin breathing leads us directly to our next formula. This is the surface area to volume ratio. Conceptually, it compares how much skin an animal has to how much internal tissue needs oxygen. The variable S is the ratio itself. A is the total surface area of the skin, and V is the total volume of the internal tissues. As an animal grows larger, its volume increases much faster than its surface area. This means that as the variables change and the animal gets bigger, the ratio S drops drastically. There is simply not enough skin to support the massive internal volume, which is why large animals cannot breathe through their skin. Before we move on, let us see this with a concrete example of a small frog. We will model this tiny frog as a cube with a side length of 1. We need to find its surface area to volume ratio to see if it can survive by skin breathing. First, we calculate the surface area of the cube, which is 6. Next, we calculate the volume, which is 1. Dividing the area by the volume gives us a final ratio of 6. Physically, this means the small frog has 6 units of skin area to supply oxygen to every 1 unit of internal tissue. This is plenty of surface area to keep the tiny frog alive and healthy. So we have seen that the small frog survives easily. This brings us to proving why giant frogs cannot exist without lungs. Let us model a giant mutated frog with a side length of 10. We calculate the new surface area, which is 600. The new volume is 1,000. When we divide the area by the volume, the ratio drops drastically to 0.6. The giant frog has less than 1 unit of skin to supply each unit of tissue. This mathematical proof shows exactly why increasing size destroys the ability to absorb enough oxygen through the skin, forcing larger vertebrates to evolve specialized internal organs. Having proven the limits of skin breathing, let us look at the actual anatomy that makes it possible. Here you are seeing a cross-section of amphibian skin. Notice the thin blue layer at the very top? This is the moisture and mucus layer that is absolutely critical for gases to dissolve. Just below the epidermis, you can see the dense capillary bed, shown as a network of red and blue tubes. The black arrows illustrate the physical process we just calculated: oxygen diffusing down into the blood and carbon dioxide diffusing out into the air. This diagram perfectly captures how the skin acts as a living, breathing sponge for small amphibians. Now that we understand skin breathing, let us look at how animals survive entirely underwater. Breathing in water is like trying to find a few grains of sugar in a swimming pool. Oxygen is incredibly scarce. To survive, aquatic vertebrates evolved gills. These are essentially high-tech biological water filters. Anatomically, they consist of thread-like primary filaments that fold into thousands of microscopic secondary lamellae, creating massive surface area. But the true genius of gills is the countercurrent exchange system, where blood flows in the exact opposite direction to the water. This brilliant adaptation ensures the fish extracts every possible drop of life-saving oxygen, allowing them to be fast and active predators. This brilliant anatomical design leads us to a way to measure its success. This formula calculates the extraction efficiency of a respiratory organ. Conceptually, it compares what goes in to what comes out. The variable E is the efficiency percentage. C-in represents the concentration of oxygen in the water just as it enters the gill chamber. C out represents the oxygen concentration in the water leaving the gills. By subtracting the outgoing oxygen from the incoming oxygen, we find exactly how much was absorbed. If C out decreases, meaning the fish extracts more oxygen, the overall efficiency E increases. Thanks to countercurrent flow, fish gills achieve astonishingly high efficiency.
Let us evaluate this efficiency with a real-world example of a swimming shark. We're given that the ocean water entering the shark's mouth has an oxygen concentration of 10. After passing over the gills, the exiting water has a concentration of just 2. We want to calculate the extraction efficiency. We use our formula and substitute 10 for C in and 2 for C out. Subtracting 2 from 10 shows that the shark extracted 8 units of oxygen. Dividing 8 by the initial 10 gives 0.8. Multiplying by 100 gives a final answer of 80%. This proves physically that the shark's gills are a masterpiece of evolutionary design. Having calculated that incredible 80% efficiency, let us look at the mechanism that makes it happen. This diagram illustrates the counter-current exchange system. Notice the large blue arrow at the top, representing water flowing to the right, starting at 100% oxygen and dropping as it goes. Below it, the red arrow represents blood flowing in the exact opposite direction, to the left. The vertical black arrows show oxygen transferring from the water into the blood. Because the flows are opposite, the water always has a slightly higher oxygen concentration than the blood it meets, maintaining a gradient across the entire length of the gill. This is what makes gills the pinnacle of aquatic respiration. While gills are perfect for water, they immediately collapse and stick together in the air. This brings us to the conquest of dry land and the evolution of lungs. When ancient animals moved to land, they desperately needed a safe, internal, moist environment to breathe. Lungs are highly elastic internal sacs designed specifically for air. Unlike the one-way flow of gills, lungs use tidal ventilation, meaning fresh air is drawn in and stale air is pushed out through the exact same pathway. Inside, they are packed with millions of microscopic bubbles called alveoli, creating an astronomical surface area hidden safely inside the chest. This massive oxygen-absorbing power is what allows mammals to maintain warm body temperatures. Because lungs use a tidal system where fresh and stale air mix, we need a new way to calculate oxygen levels. This is a simplified version of the alveolar gas equation. It shows that oxygen in the lungs is always a balance between fresh air coming in and waste gas pushing it out. The variable PaO2 is the actual oxygen pressure deep inside the alveoli, available to the blood. PiO2 is the oxygen pressure in the fresh air you inhale. PaCO2 is the carbon dioxide pressure your body dumps into the lungs. Finally, R is the respiratory quotient. If carbon dioxide production increases, the available oxygen in the alveoli physically decreases. Let us calculate this balance for a terrestrial mammal resting at sea level. We're given that the inhaled fresh air has an oxygen pressure of 150. The alveolar carbon dioxide pressure is 40, and the respiratory quotient is 0.8. We want to find the final effective oxygen pressure deep inside the lungs. We use the alveolar gas equation to subtract the effect of the waste gas. First, we divide 40 by 0.8, which gives us 50. We then subtract this 50 from the inhaled pressure of 150. The final answer is 100. Physically, this shows the inherent trade-off of lungs. Mixing stale air reduces the driving force of oxygen.
We have covered a tremendous amount of ground today, so let us review our key takeaways. First, we learned that all respiration is driven by passive diffusion, and Fick's law dictates that animals must maximize surface area to survive. We saw how small amphibians can breathe directly through their moist skin, but are strictly limited by their surface area to volume ratio. We then explored how fish gills use a brilliant countercurrent exchange system to extract oxygen from water with unmatched efficiency. Finally, we saw how lungs pack millions of alveoli into the chest cavity, providing the massive oxygen supply needed to conquer dry land. You now understand the incredible evolutionary journey of vertebrate respiration.